All right, so today we're talking about Kubernetes resource management and specifically CPU limits. Just by a raise of hands, who here is running workloads on Kubernetes? Okay, and who here is using CPU limits? Okay, so I got a few people here to convince. And my hope is that by the end of this talk, you will remove them all. And I'm going to go through and I'm going to show you why I think that's the right option. And I'll speak about caveats for when it's not the right option. Well, to get started, I just want to start by saying that this clicker isn't working. Okay. Yeah, so I'm originally from New York, where I grew up, and I really like London compared to New York, much cleaner city, a lot of attention to the details. And on the way over, I noticed this thing on the public transit here on the tube called priority seating. And I'm sure all of you except for me know what this is, but now I do. And what priority seating is about is, on the one hand, making a seat available for the people who really need it and people who can't sit elsewhere. On the other hand, still making it available for everyone if no one has that special need. And really that's what we're going to talk about in the cloud context, in the Kubernetes context, and how on the one hand, you can guarantee performance for your applications on Kubernetes, and you can guarantee that things aren't overwritten or don't have performance stealed away by other workloads. And on the other hand, you can make sure that compute doesn't go to waste. And that if people need it, then they can take advantage of extra capacity. And really all of resource management on Kubernetes comes down to 4 numbers, the 4 hardest numbers to determine on Kubernetes: the CPU request, the CPU limit, the memory request, and the memory limit. And fortunately, there's a lot of consensus around how you set 3 of these numbers. You have to go and you have to do the work, but 3 of these numbers, everyone in the world will agree on how you set them. And if you get them wrong, you're going to have bad utilization, you'll have bad performance, you'll waste cost, you do all sorts of things that you don't want to do, but everyone agrees on how you set them. And it's that last number that is the topic of a ton of controversy, and that's what we're going to talk about today. So just a little bit about me and why I'm here doing this talk and not someone else. So I'm the co-founder of Robusta. We take the data that's already in your Prometheus and we build a full observability platform for Kubernetes on top of that existing data. And we get a lot of questions from our customers and from our open source users about saving cost on Kubernetes and why are pods suddenly CPU throttled and why are there issues with P99 latency and how you should set request and limits. So we've had to really dive into this topic a whole lot. And a few years ago, I wrote a blog post, the first result on Google Now, after the official Kubernetes documentation on limits. And since then, I've heard from so many people, so I'm going to try and cover some of the common objections that I hear and going to cover things that I've heard from really all the discussion that this post has generated. And I hate theory, so I'm not going to talk about theory. I'm going to give you a fake example, but that is in some sense a true story because it's happened in some variant to many, many companies and possibly to some of you. So I'm going to tell you a true story that never happened, and I'm going to use that to illustrate the problems. And then we're going to actually go and test it out so that people don't have to take my word for it. And then I'm going to show you some caveats at that. Okay, so let's get started with an imaginary application. And the real problem that I have, I go to a decent amount of conferences, and I come back and I have lots of socks. And you'd think that when I do laundry, I end up with 50 pairs of matching socks, but instead I have 100 pairs, 100 individual socks, and none of them match up. So I've decided to do something about this, and I've decided to create what I call Tinder for socks, which is an application where I can connect with other people in my neighborhood, and we can swap socks to find the matching pairs. So I write this application. Of course, I'm going to run this on Kubernetes because it has to be highly scalable. And socks are HIPAA compliant, and this is medical data, so I need to have different applications for different regions. So I'm running this all on Kubernetes. And here's the architecture. I have a pod, and it's called the sock server. And it runs on the node, and I have a bunch of instances of that. And everything is fantastic. And I am running this application and probably not making a lot of money, but running this at scale. And one day I start getting complaints that there are all these performance problems and people cannot match up the socks. And I go and I look at it, and what do I discover? Well, my backend team, they've been working on this really cool feature called SockGPT, where they take all the data about the socks, and they run this machine learning training, and then they can suggest socks that don't exactly match but will be a great fit. And they can do all this cool stuff. And they've been training this big, giant machine learning job on the same cluster, and it happens to be running on the same node. And now it's stealing all the performance from my sock server. So all over the world, meaning me and like 3 friends, are accessing this sock application, and we're going in, we're trying to use the app, and we're clicking, and it's taking forever, and it's loading, and we can't match up the socks, because on the same node, I have this noisy neighbor, and this sock GPT training job is stealing all my resources. So who here has ever had a problem like this? Fantastic, and that's why you all set limits. Or took a different approach. So that's what I'm going to dive into. So option number 1, and what most people do, is they look in the Kubernetes documentation, and there's a feature there called CPU limits, and they do the natural thing, and they say, okay, well, this sock GPT training job is taking up all the CPU, so let's stop it from stealing up and using up all the CPU. So what we do is we put on a CPU limit, and we're saying this sock GPT training job is now constrained, and it cannot use, let's say, more than 1 CPU. And this does not solve the problem. And the reason it doesn't solve the problem is because tomorrow my team spins up 3 more of these for each of those HIPAA regions or whatever, GDPR regions, whatever I have to do, because this is multi-tenant and whatever. And now actually I have 3 of those running on the same node, so even though I've constrained their resource usage, they're still stealing away the memory from the sock server. So we've tried to fix this problem of sock GPT stealing resources from sock server by limiting sock GPT. In other words, I have a problem with my neighbor, so I didn't do any self-introspection. Why is I went and I limited my neighbor? And what I'm going to show you is that actually the correct way to fix this is the complete opposite. And the way that you can do this actually is without CPU limits at all. What you can do is you can fix this with the CPU request on sock server. So on Kubernetes, like I said before, there are only 4 numbers that matter when it comes to really resource allocation and cost optimization and getting everything right. And I realize now I'm halfway through the talk, and we're probably only 5 minutes in, so we may have a live time at the end for questions. So there are only 4 numbers that matter on Kubernetes, and those numbers are the CPU request, the CPU limit, and the memory request, and the memory limit. And that controls all of your utilization and really all of your spend ultimately, and whether you have pending pods or not. And just to remind everyone of the limit of the difference here between a CPU limit and a CPU request, is a limit says you may not use more than 2 CPU. And what a request does is a request says I need 1 CPU or I need 2 CPU. And it's essentially setting a lower bound on how much resources will be available to you. And there's a big misconception. People think that CPU requests are used at scheduling time for Kubernetes to go and to figure out where to put the pods, and then Kubernetes forgets about them. That's actually not true. In fact, if you set a CPU request, so in this case, if we ignore the sock GPT training job, we don't touch it. We go that sock GPT training job, we remove the limit, we don't put anything on it. And instead we go to the sock server and we correct the allocation for sock server. And we correct this and we put on the big CPU request for sock server that matches what it needs, then that amount of compute will be guaranteed for sock server and no one can take that away. So given that it's a relatively small audience today, and it's great to see all of you, and given that I am doing this much faster than I anticipated, I'm actually going to do something a little unconventional and stop for a moment halfway to see if there are questions so far. Yeah, go ahead.
You said you get too late. I was just wondering, what's the point of limits then? But I think you said you get to that later.
Yeah, I'm going to cover it at the end in the caveats. But the point of limits are for cases where you want to make sure that an application does not use above a certain amount. It's not for a case, like everyone thinks, where you want to make sure that an application can use above a certain amount. So it's a two-sided problem, and you have to decide, like most people tackle this problem by trying to restrict your neighbor. But no, the problem isn't that your neighbor's house is too big, it's that your own house is too small. The problem is, and if you go back to that priority seating, the solution to make sure that people with wheelchairs have a place that they can stay on the tube is not to say no one else is allowed to be here. It's rather to say you get the priority and this place is allocated for you. But if you're not using it, then other people can have it. Yeah?
Quick dumb question. Can you explain a little what the units are for the CPUs? I've never really figured out that, what the number actually is. Just how can I think about that as a
Yeah, absolutely. So the question is, what are the units on CPUs, which people actually don't cover very often. It gets skipped over. There's this magic number you put there, and that correlates with the virtual CPUs or the physical CPUs if you're running on physical hardware. So the way to think about that, and there are many abstraction layers in between, but the way to think about that is imagine you have like an old Intel i2 or i whatever, right? And you get a computer that has 2 CPU cores, then one would be one of those CPU cores, and 1.5 would be 1.5. So if you have a 2 CPU machine, or virtual machine, or whatever your node is, then 1 CPU would be half of that. And the reason that this is so tricky is because one, not all virtual machines are equal. So like 1 CPU on a Pentium i2, or I don't know, I'm like making up machine names, but 1 CPU on a really weak machine is actually not equivalent to 1 CPU on a really strong machine, but from Kubernetes perspective, they are. And the other reason it's really tricky is, let's say you have a machine that has 2 CPUs and you can say, I can have 1 CPU. Well, that means you get 50% of the compute, but 50% over what period of time? 50% over a 1 second period, 50% over a 10-minute period. And because of that misunderstanding, because of that nuance, then when you put on limits, then I'm not going to go into this in depth, but you mess up P99 latency because of how that's computed. I'm going to move on now, and then we'll take more questions later on. Okay, so what we want to do, just to recap, is we have our SAC server, and we have the SAC GPT, and we want to make sure that SAC server gets the resources it needs, not by putting any limit on SAC GPT, but by putting an accurate request on SAC server. And the common misconception, and the argument that I've had with countless people online and in person, is, well, do requests really guarantee resources? So if I go to SAC server, let's say I say SAC server needs at least 2 CPUs, and I put in a 2 CPU request, and I do not put on a limit on SAC GPT. Am I really guaranteed 2 CPU? Am I really protected from these awful neighbors that are going to go and try and use up all the CPU? And there is no better way to answer that question than to prove it and to show some YAML. So that's what we're going to do. So here's the scenario, and then I'll show you the YAML. We have a node, and we have just one node. It's my laptop over here, which is running a kind cluster. And on that kind cluster, I have a node with 4 CPUs. So that's the total capacity. I have only one node in the cluster, so everything is going to run on that one node. And then I've got the SAC server, and SAC server will want 2 CPUs. And SAC GPT training job will want 4 CPUs. And I'm not saying any requests, and I'm not saying any limits. When I say what they want, I mean I've set it up so that they're both running a stress test, and they're both burning up these precise amounts of CPUs. So SAC server will try and burn up these 2 CPUs, and SAC GPT training job will try and use up 4 CPUs. And they will obviously both not succeed at doing that because it's a 4 CPU node, and the sum of these 2 is 6. Questions about the setup? Okay, so let me show that to you. And I'm just going to go over here, and I'm going to run kubectl get pods. Okay, and I got SAC GPT, and I got the SAC server. And I'm going to run kubectl top pods. And we can see here that I have my SAC server, and it wants to use 2 CPU, and instead of, let me just clear that, and instead of getting 2 CPU, it's getting 1.5. The units here are in milli-CPU, so I actually lied to you before. It's not in CPU, it's in milli-CPU. But when you put it in the YAML, it is in CPU. So this is getting 1.5, and it's not getting the 2 resources it needs. So again, in our imaginary application, and for some reason I actually wrote that application last night, and I wrote a demo of it, and I realized we had nothing to the, showing you how you can try and match up socks. We didn't actually add anything that you would take home, so I decided to cut it out. But in our imaginary scenario, then this application now is not performing well because it doesn't have the resources it needs, and it's going slow. And let me show you the YAML. So first, here is SAC GPT, and I'm just burning up 4 CPUs. And no limits, nothing. I have it commented out. And here is SOC server. And is going, and I'm actually trying to burn through 2.5 CPUs, but I put it as a little bit extra, because otherwise I won't succeed in burning the exact amount I want. And I have no requests, it's commented out. So in this scenario, like you just saw, I'm getting 1.5, I'm not getting what I expect. So instead, I'm gonna just make one change, no limits added, nothing. I'm gonna just put on here these 3 lines. I am giving SOC server a CPU request of 2 CPUs. And we'll have to wait a minute for this to update. And I think you guys can guess by now what's gonna happen, or I'm gonna have a really embarrassing demo and everything I've said is wrong. So we hope I didn't mess up the configuration. And we're gonna have to wait a little bit for that to finish terminating. So I'll recap in the meantime. So we have here the node with 4 CPUs. We have SOC server. It wants 2 CPUs. Before it had no request, got 1.5. We have SOC GPT, which has no limits and is trying to use up all 4. And if we go back, okay, these are both running now. And I have to wait about another 10 seconds for the metrics to update. But you can already see actually that it's starting to stabilize, and SOC server is not getting 1.5 anymore, it's getting nearly 2, and that will stabilize. So here's the proof. Yes?
So it took the command as a precedence? Because I have seen in the life that you have taken the commands, then after that the resource block you have changed it. So it means it has overwritten the command sections?
Can you explain?
Yes, can you open the binary, please?
The YAML?
Yeah. I like it how you opening VI.
Oh, of course. Yeah, so, okay, to explain, so I didn't,
The arguments, so it took the resources, it took the precedence over the arguments. That means you are passing it as a command.
it's just about the simulation. The resources is what I'm trying to burn. So I'm not actually running here the SOC server, because it's hard to get my HTTP server for SOCs to actually reach a full 2 CPU. So I'm running a stress test. This is just about the way I'm testing it and simulating it. But I'm running a pod called program stress that will burn as much CPU as I tell it to. So it's trying to burn 2.5, and it won't be able to burn 2.5. So before it was trying to burn 2.5, and it ended up burning 1.5. And then when I added this request, you can now see it's burning 2, because that's what the request guarantees it. Okay, other questions?
And so if you increase the 2 to 2.5 there, will it just take what it needs then?
Yeah, let's try it. And again, there's like a nuance here with program stress. If I tell it to consume 2.5, it's actually going to consume about 2.4. But it's due to how I'm actually, it's not due to the request, it's due to the way that it's consuming the resource. But yeah, let's test it out. Kubectl apply minus f SOC server. And then we're gonna have to wait again a little bit more to see this, but you're gonna see that SOC server will get 2.5. So I'm gonna take another question while we wait for that to update. Yeah.
Sorry, I was just going to ask if you could open the YAML 5.5 for the other deeper.
Yeah, of course. SOC GPT, right? This is trying to burn 4, and I commented out their limit.
Yeah, that's fine. I was just double check.
Please, guys, check me on this. I'm gonna put this online afterwards, and I can already tell you that I'm gonna get a lot of comments from people who are saying that it's wrong. But then they'll take the files and they'll check them themselves, and then they'll say it's right. I've been through this before. Yeah.
So if you did uncomment that limit, you're just saying, you're necessarily crippling the GPT job when there would be more resource available, maybe turned off the other certain models.
It doesn't matter. That's the point. If I uncommented that and I put on the limit, then I would artificially cripple the SOC GPT so that even if there's extra compute, it can't use it.
Yeah.
And I wouldn't actually benefit. The SOC server all the time. I would benefit it like in certain scenarios, but I wouldn't even be able to guarantee that it's benefiting. The correct way to fix this is to increase the request on Slack server, and I will guarantee a fix for Slack server all the time. The one nuance here is like you have to have like requests that are accurate, but I would say that it's no better, like if you use limits instead, then you also have to have limits that are accurate, so you're no better off. So let me show you though, I wanted to show you how now we should be consuming 2.5. So kubectl top pods, and Slack servers will have about 2.5. Did I apply that file? Let me see. Yeah, I put in a request of 2.5. Just to make sure it can actually burn the right amount, I'm going to increase that a little bit so it's not held up on. Okay, yeah, so I'll resimulate that. But more questions?
Does this mean some GPT can't go take, like if 90% of the time stock server only really needs 1 CPU or 1.5 CPU, the fact that we've requested 2, does that mean that stock GPT can't get that?
No, that's the beauty of it. That's the beauty of it. The beauty of this is that on Kubernetes, requests function as soft limits. So you will be given first, it's really back to that priority seating. You will be given the first priority, but if the access capacity is available, then you will be able to have the access capacity. Yeah.
Okay, so it's soft request, so you've got, let's say, a 6 node, and you request 2 on both. I'm trying to think of the situation. Basically, if one node starts using, it's only requesting 2, but it's scared, it's like particularly busy, and now it's using 4, that's a soft limit. If some job then comes to schedule along, what's Kubernetes going to do about placing that?
Fantastic. So the question here is, okay, I requested 2. In practice, there's excess capacity, so I get to use 4. And now someone else comes along who needs those extra 2. So what happens, right?
Yes.
And the answer is, it just gets taken away in an instant. And this is why everything I say today applies to CPU and it doesn't apply to memory. Because CPU is what's called a compressible resource. I can give you CPU 1 minute and then I can take it away the next moment. And it's like if we spend time today and we go and we drink a beer, that doesn't obligate me to drink beers with you tomorrow. And if we don't drink beers tonight, then you can't go back tomorrow and say, well, now I'm going to use the beers from that. It's time. That's the thing. The resource here is time. So if you don't use this, it's not like you're saving the resource to use forever. The time has passed by and the resource was unused. You can't go back in time. But all this is not true for memory, because for memory, let's say I have an extra gigabyte, and I give you an extra gigabyte, and now I want it back for someone else. I can't take back the extra gigabyte without killing the application. But on CPU, I can, because with CPU, you're just at every single, every 100 milliseconds, or whatever, every scheduling epoch, then the kernel is deciding who to give it to, and who it gave it to in the previous epoch doesn't have to impact who it gives to in the next. So I'm going to just go on, so I'm sure we fit the time. And then come over and I'll show you also the 2.5. So we'll see the scenario on that. I just want to make sure I finish on time. Okay, so here are the caveats. So limits are useful for memory, and limits are useful for stress tests, right? You want to stress test how your application will do when there isn't excess capacity. Put in the limit and go ahead and test that. That's useful. And there's another case where limits are useful, which is to stop people from getting extra compute. So this ties into what was asked earlier. So I have a friend, for example, who he works at a company, I won't name, but that is a very successful startup now. And they run something that's compute heavy that they sell to customers. And their customers come and they pay for them for certain amounts of compute. And he said to me, well, Natan, we use limits because let's say I don't use limits. Let's say I don't use limits and our customers are paying for 2 CPU and they come now and there are no limits in place and they benchmark us, and at the moment they benchmark us, then they got 4 CPU. And then tomorrow, they're not going to get 4 CPU because it's not guaranteed, and they're going to go and they're going to say, you guys have a 50% decrease in performance. So I don't want to give them extra excess capacity if it's there. So that's the case where you would want a limit. You want to put on a hard limit. And then the final caveat here is this all works if you have CPU requests. If you don't have CPU requests, then you don't have limits, you have the worst of both worlds, because then It's just willy-nilly what happens. So you need to have requests in place. Your requests don't even have to be 100% accurate. That's the nice thing, because it kind of balances itself out. Like one moment, one application is spiking, then the next moment, another one is spiking. And if you do that, then this approach can work. And if you look online, you can actually find a lot of companies that run this way in production. And people are doing it. So like there are very large companies with very large Kubernetes instances that are running this way. Tim Hockin from the Google Kubernetes team is on the record saying that this is the right way to do it and that you shouldn't set limits for most applications. So this can work, and I would recommend people consider it. And just make sure you get the request right, or relatively right. Any final questions?
So then done. With your two applications, if you put requests for both, 2 on the SOC one and 4 on the GPT one, and you've got your one node laptop.
Pending.
Oh, so it wouldn't schedule.
It won't schedule. Kubernetes won't, because Kubernetes, that's the thing. A request is a promise. A request is a hard contract. When you put a request of 2 CPU, then Kubernetes is saying to you, guaranteed, I will promise that you will be put on a node with 2 CPU, and I will not put you on that node if there's not enough room, and at runtime you'll be guaranteed that. And if anyone is here who like writes Linux kernel drivers, then you can catch me on some small caveats where it won't be exactly 2. And they're very minor edge cases, but you're more or less guaranteed 2.
Cool, thank you.
Yep.
How does this work under the hood? Is it U-limit or like niceness? What is it that it's doing that is actually happening at the kernel level?
So it's let's go into afters and we can look at it, but it's CFS shares and CFS quotas, I think. I always get them mixed up. I think this is shares and then quotas are limits. But it's, and I'll say one more word here about like, that's kind of super technical on this, but the problem is, and the problem with limits and the problem that this is so painful is because let's say, again, let's just say you have a 2 CPU node and you have an application that gets 1 CPU. That doesn't mean you're guaranteed 1 CPU at every point in time. It means that you're guaranteed 50% of the CPU over a period, and those periods are, let's say, 100 millisecond periods. So let's say you have an application that's average CPU usage, or its CPU usage is always below 50%, and you give it 1 CPU on a 2 CPU node, and you say this needs 1 CPU, and you put a limit on that as well, and you say, okay, it doesn't need more than 1 CPU, you will be CPU throttled on most real case workloads. Because the pattern in most real workloads is not, I'm going to use 50% of the time, like 50% of every 100 milliseconds, I'm going to use the CPU. The way most real workloads work is I will use 500 milliseconds of CPU straight and then do nothing for another 500 milliseconds because an HTTP request came in and then didn't come in. And what that means is if you're looking at the way that works with CPU limit on like 1 CPU and a 2 CPU node, then it means you will run, if the scheduling period is 100 milliseconds, you will run for 50 milliseconds, you will wait for 50 milliseconds, you will run for 50 milliseconds, and you will do that 10 times and have really bad latency, even though your average CPU is exactly equal to your limit. So that's why this is so tricky and unintuitive.
So I'm not a huge case user, but I'm just curious. Is there a way of setting like core affinity or pinning in Kubernetes?
Yep.
So that you don't mess up your cache allocations and stuff like that?
Yes, there is. So if you do like dedicated cores or you do pinning, then like you don't need to listen to anything I'm saying here. You're operating in a different realm.
Yeah, I was just curious though if that was something that people did.
Yeah, people do it. People do that when they need to really get extra performance out, and then you're not really using requests or limits.
Yeah.
Any final questions? I think we're over time, right?
You can run another couple more minutes if there's questions.
Okay. Yeah, so any other questions?
If you could explain on the request and limits.
Yeah, so a request is saying, I will get first priority on this, and Kubernetes will only put me in a place where it can guarantee that I get first priority. And then a limit is saying, I will get no more than this, no matter what, even if it's available.
So that means it takes care of the quota, and it's, say, 5 is the request, and 2.5 is my limit. So it takes here 5 and gives 2.5.
Yeah, exactly. Think back to that priority seeding. This is really about that priority seeding. And the reason all this matters at the end of the day, like you guys are going back to your companies tomorrow and going back to where everyone is working. The reason why all this matters is we live in a world where most companies have the worst of everything. There's a statistic study that people over-allocate CPU on Kubernetes by 69%. So most people are paying 69% extra for their compute on Kubernetes. How many things can you do that will reduce the cost by 69%? All you have to do is get those requests right. And on the other hand, at the same time that that's happening, people have pending pods, and they auto-scale the clusters, even though they're at like 20% utilization, but they still have pending pods, and then they still end up having really bad latency, because the applications are running, yeah, they're running like, they're getting the right allocation of time, but it's distributed all wrong. So they're running for 50 seconds, then stopping, then running for 50 seconds. So you have the worst of all three worlds. You have something that's really expensive, right, and is over-provisioned, and yet you still have pending pods, you still have scheduling issues because it's being distributed wrong. And on like the third side, then you have horrible latency, and you have really bad performance. So it's like everyone, not everyone, a lot of people are doing it right, but it's very easy because it's so unintuitive, it's very easy to mess it up and to shoot yourself in the foot in a lot of ways on this. So I hope this has been useful, and I'm on LinkedIn, and I'm on Twitter, and I'm Natan Yellin. I don't know if that says it somewhere, but it probably says it on the talk. I'm on Twitter too, so feel free to reach out, and if it's okay, I'll plug, we do have an open source tool that looks at Prometheus data and tells you how to set your requests as well. Again, the data is all there. Like how many things can you do that will save yourself 69% in your cloud bill? So I encourage everyone to really dive into this, and feel free to reach out if you have questions. Thank you.